Hello everybody, my name is Daniel Abshire. I'm talking on behalf of Group 12 today. Our project is ThinkNav, the target acquiring and tracking quadcopter drone. Our four-man group consists of myself, an electrical engineer, Vincent, another EE, Garrett, a third EE, and Daniel, our computer engineer. To begin and introduce our project, ThinkNav is a vision-based machine learning navigated drone which tracks vehicles using an object recognition software utilizing the on-drone camera and a data set which we have curated. The drone locks on and pursues the target after identifying it. The drone is able to follow at an appropriate pace for pursuit of a vehicle and is able to maintain this pursuit over an extended period. Our motivation for this project was to design and create a device which functions as a middleman between foot, car, and air-based pursuit, which eliminates the interference of ground-based obstructions, outpaces foot-based pursuit, possesses more maneuverability than a car, and avoids the downsides of costly air-based pursuit, such as response time. In addition, we were motivated to make this device function as a beacon to follow during pursuit if, say, visual contact was lost with the target. The addition of lights as well as a sound emitter were also intended to allow for the device to be more noticeable and to ensure it remains an easy beacon to follow. The design goals we set out for this project were as follows, split into two categories, hardware goals and software goals. The goals for the hardware of the drone itself were to construct the drone that it may fly at speeds of up to 20 miles per hour. Also, to construct the drone in a way where it can navigate through turns, elevation change, and directional control, allowing it to be able to fly in such a manner that it can adequately follow the target. In addition, the drone was constructed in order to be able to operate for a flying time of 10 minutes. As far as the software goals go, the software is able to detect the pre-selected target of a car in the area the drone is searching. It is able to reacquire the target if visual connection is ever interrupted or lost, as well as feed all of the navigational data gleaned from the camera and the sensors in the drone to the flight controller, which allows for its autonomous navigation. As far as PCB specifications go, our group met the established requirements and expectations of the department by utilizing a printed circuit board to route our peripheral systems, as the primary systems of our machine learning is accomplished on the Jetson Nano, and the flight control is accomplished on the flight control board. We designed a PCB which routed directional indicator LEDs, which would allow us to be able to tell whatever direction the drone is facing, and are directionally color coordinated, indicating visually the direction in which the drone is traveling, while also functioning as a way to make seeing the drone easier. In addition, the sound emitter is also ran through this PCB, which manages its integration with the system so that it may beep whenever the drone is in function, also allowing it to be noticed and followed in a way that is non-visual. The PCB design ended up being two separate systems operating in parallel. The light system, seen around the outside of the PCB design, relied upon a 9-volt input in order to power all four directionally colored LEDs, attached at each corner of the PCB. This connection was severed by 2-pin inputs to allow for the switch or other controllable on-off device to toggle whether the drone is being used. In the interior of the PCB is the sound emitter system, which operates using a 2-ohm speaker, as well as an NE555 timer module, in order to utilize it to create a consistent tone out of the speaker. The sound emitter module also operates by using a 9-volt input and 2 open pins in order to integrate a switch or other module for its operation. The primary sensor used in the system was the camera. The camera used for the drone was one of the most key components of the whole project, being as the entirety of the software hinged on the ability to perceive the surroundings. The camera had to have high enough frames per second in order for the drone to be able to responsively navigate in a timely fashion. In addition, the resolution of the camera was vital for accurately observing the perceived area. If the resolution was too low, the effectiveness of the object recognition would suffer, especially at the ranges we wanted to test at. Finally, the weight of both of these components was very important to keep in mind. In order to make effective use of the battery life of the drone, these components had to be lightweight. Overall, we settled on a camera with 2 high frame rate cameras at lower resolutions and one higher resolution camera at a lower frame rate in order to achieve both goals. This camera was specifically designed for use in object recognition, so it was a good fit for the use we intended. The Pixhawk is half of the brain that makes up the functionality of the drone. The Pixhawk is a flight controller by design, which is a microcontroller specifically made for flight commands. It takes the commands given by the NVIDIA Jetson and converts them into flight controls. For example, if the Jetson gives the command to side shift left, the Pixhawk will lower the RPMs of the left side motors, so that way the drone will drift left. The Pixhawk is designed to take commands from computer code, which makes it one of the prime choices for autonomous flight missions. It has accurate GPS built in, paired with precise balance sensors, which gives us pinpoint precision, which allows us accurate movement through the air in 3 dimensions. For our microcomputer, we chose to go with the NVIDIA Jetson Nano. The Jetson Nano is a very powerful GPU that is used in many machine learning, more specifically computer vision projects. It outperforms industry-leading microcomputers like the Raspberry Pi in image processing, given that it is an actual GPU and has higher processing capabilities with a 128-core Maxwell GPU at 921 MHz. This GPU will allow us to perform our goal of object detection and tracking very effectively, as it gives us the ability to deal with more real-time image processing much more efficiently.
In order to complete our objective, our team agreed that we need a minimum of 10-minute flight time was required to give us enough time to take off and locate the vehicle in order to successfully track it. We added a 20% buffer to this, so this brings us to 12 minutes. With this in mind, we first needed to figure out the final weight with all the parts and equipment on board. In order to encompass all of the equipment, we needed a large, strong frame with the lowest possible weight. We ended up choosing a durable plastic frame with carbon fiber legs. From top to bottom, the main contributors to the weight were the frame, the computer, the battery, and the motors. The only thing we're not certain of at this moment is the printer board's final weight, but it's unlikely that it's going to have a high enough effect to mess with the results that we had. We did some research on lighter component variants in order to find the highest efficiency at the lowest weight. This includes things that were not inherently obvious at first, which includes the type of casing on the battery. Switching it from a hard to a soft case made a 200-gram difference just on its own. This discovery allowed us to up the battery size from 6,000 milliamp hours to an 8,000 milliamp hours without affecting the weight difference, which gave us a few additional minutes of flight time. In grand total, we calculated the drone is going to weigh about 1,500 grams with the battery included. With the weight in mind, we calculated the thrust we needed to properly take off for lift and flight. The drivetrain is comprised of 3 main parts, which are the props, motor, and battery cell count. At a minimum, you need at least twice the weight and lift thrust in order to support flight, so this puts us at about 3,000 grams of lift thrust. The interesting thing about building a heavier drone in comparison to a smaller, lighter racing drone is that we need to keep the RPMs of the motors close to the number we need instead of as high as possible. This is due to the torque the motors experience in order to spin larger, heavier blades. If the motor is forced to spin faster than the stator can handle, it will cause mechanical failure. So in order to balance this, we needed to make sure that the propellers were the correct size and that the motor at maximum RPMs would not overexert itself, and that the battery cell count will not supply too much voltage. The cell count is especially important because each cell supplies about 3.7 volts to the motors. The RPMs are calculated by multiplying the kV motor rating against the voltage supplied, so each cell added gave us 3.7 RPMs. With this being said, we found in the simulations that at 4-cell count battery, the RPMs were way too high to spin 10-inch blades, and at the higher speeds, we wouldn't be able to sustain flight long before failure. On the other hand, if we used 2-cell battery counts, the RPMs were so low that we couldn't get sufficient lift. This gave us an ideal drivetrain configuration of 10 2-blade props, 10-inch 2-blade props, paired with 2212 920 kV motors, and a 8,000 milliamp 3-cell battery. This gave us a thrust to weight ratio of 2.2, which puts us at a total of 3,300 grams of lift thrust. After hand calculations were done, we used a program called eCalc in order to test all combinations of parts to see if they matched. This program gave us valuable data so that we could properly compare parts in order to make sure that the quadcopter had optimal flight time. We compare and test various parts such as prop blade count, blade thickness, motor size, battery size, and motor number configuration. With this in mind, through thorough research and available parts and configurations, we were able to exceed our simulation goals and achieve an 18-minute flight time, which gives us more than ample room to complete our objective. Our goal is to have the drone assembled and in the air by the third week of February in order to give us enough time to test its flight capabilities and to work out any bugs we run into before our March review.
Next, we will be taking a look at our requirements and needed functionalities. Below is our requirements table. Here we can see all the different components of our drone and the requirements associated with them. First, looking at unmanned quadcopter, we were able to achieve all the requirements we set out for. We were able to fly the drone autonomously in the area specified, as well as fly it at the height specified, and even achieved a higher height than what we originally expected. The drone does flies a little under the 20 miles per hour in all directions, but is still able to consistently track and follow the cars. Next, we will be taking a look at the computer vision model, and this basically relates to the object detection and the accuracy of it, which we were able to achieve a pretty high accuracy, and we are able to consistently detect that a car is a car or that a person is a person, which was another goal we had. Basically every time that they are in the frame, so that was a great achievement of ours. And we were able to take in the video input at the speed and the quality we wanted to, so that was a big plus for us in getting everything to work appropriately. Moving on to our needed functionalities table. Here we can see the components again, as well as the functionalities associated with it, beginning with the unmanned quadcopter, which we set out to basically make it fly autonomously, making it make and follow its own predetermined path, which it did successfully. Next, we move on to the computer vision model. Here, our goals were to basically take input, real-time video input, as well as, detect the car and maybe even detect the person. So we were able to achieve a lot of these functionalities. As you can see, we mentioned that we wanted to be able to detect the vehicle license plates, but we were only able to get it to detect cars and people as of now. Next, we move to our real-time video input. Here, we were able to successfully accomplish our goal of locking onto, tracking, and following the desired target, as well as doing that with little or no interruptions or interference due to vibrations or shakiness. So that was a big plus for us because we were able to get quality footage from our onboard and see how all the detection happens. Lastly, the GPS tracking. We successfully were able to calibrate and use a GPS, returning the drone position, as well as allowing it to fly autonomously and follow the vehicle once it's found. And it also allows us to return the position if the drone doesn't know what to do. So that was a big plus. Next, we have our tracking algorithm. For our computer vision model, we decided to use Depth AI. For tracking, Depth AI uses KCF, which is shown below. Originally, we had also planned on using KCF since we did a lot of research and we came up that it was better than most other tracking algorithms out there in the market. This is because it's very efficient, it's low cost, it's very easy to implement, and the most important part was that it pairs really well with a lot of object detection algorithms. While it does have some disadvantages with occlusion or fast-moving items, these are things that could be taken care of through object detection. So below, you can see how KCF works. It basically takes an object detection and assigns it a confidence and a bounding box. So based on this, it will then predict the tracking output, which will allow it to come up with its own predicted path and keep tracking the correct target. Moving on to our software goals. Our initial software goal was to implement a computer vision algorithm that can identify and track 3 different cars in a parking lot. While we were able to successfully implement a computer vision algorithm that is able to identify a car in a parking lot and actually follow the car, we weren't able to get it to detect the 3 different cars we wanted. At the end of our project, the capabilities of our drone were as following. We were able to object detect a car, even a person, and once it was detected, the drone would then go closer to a specified distance and keep that distance as it follows and tracks the target. We did this by using Depth AI, as mentioned previously. This allowed us to create a drone that was fully autonomous and that completed the goals that we set out for it to.
Hello, my name is Garrett Rocks, and I was primarily responsible for developing the software stack. The software stack used was able to implement all the different devices on the ThinkNav drone and allow them to communicate with each other in a way which was able to achieve the desired functionality. The NVIDIA Jetson serves as the main brain of the drone, allowing all the other devices to be able to be orchestrated by the one computer. The main Python code runs on this device. The OakD Lite has an onboard video processing unit, VPU, which runs Depth AI code in order to handle the stereo depth perception data and incorporate that with the YOLO object detection, which is also running on the OakD Lite. We use Mavlink to connect the NVIDIA Jetson to the Pixhawk, which is the flight controller. Mavlink is a common communication protocol used in serial communication between a drone and a ground station, which on this case was actually on board the drone. ArduPilot runs on the Pixhawk, the flight controller. ArduPilot is a software developed by ArduPilot, which is able to handle the Mavlink commands and control the motors and read data from the GPS and IMU in order to stabilize the drone and allow it to execute commands properly. All of these devices were able to be orchestrated together by the software stack. The main Python code first waits for the device to be put into guided mode, which is a command sent by the controller by manual input. As can be seen in this video, when guided mode is activated, the drone then initiates the main Python loop, which first waits for a target lock. And you can see that the car is too far away to be detected until right now, when it switches into tracking mode. It is now maintaining a distance of 6 meters and trying to maintain an altitude of 2.5 meters, which is all handled in the main Python code. You can see that it attempts to center its video frame on the detected target, has some trouble doing that here. You can see the lighting seems to mess with it a little bit, and it has trouble maintaining its altitude. But this is an example of the tracking working as desired. And you can see here in the test, there's actually a moment where the camera gets bumped and ends up pointing downwards, which happens here in a sec. And even though this is not desirable, you can see right now it actually gets put into its searching mode, which is when it spins at a slow rate until it acquires a new target, and then goes back into the tracking mode. So even though the camera was bumped, the code functionality still was as desired. In order to fulfill the goal of detecting cars and people, we are using an object detection algorithm which is run on the DepthAI OAK-D Lite camera. The object detection algorithm that we ended up using was Tiny YOLO v4, which is a scaled down version of YOLO v4, which sacrifices accuracy for speed for use in embedded systems application with limited computing power. We were able to run this at about 26 frames per second on the Jetson Nano microcomputer, while also using the DepthAI OAK-D Lite camera, which had the onboard video processing unit, which sped up the processing. The YOLO v4 algorithm works by separating an image into a grid and drawing potential bounding boxes along with the confidence of these bounding boxes, and combining that with a class probability map, which is spread out throughout the grid. And those are combined to make the final detections used by YOLO. It's considered a very fast and accurate algorithm.
To simulate the drone performance, we used a program called eCalc, which takes all part performance information for all the parts and gives us estimated flight data based upon all the given parameters. This information included thrust ratio, flight time, battery consumption at different speeds, and motor efficiency. When we tested this, we did this purely with RC only, just to make sure that we had all connections correct and that everything was functioning properly. In order to make sure that the drone performed close to the simulation, we tested it based on its hover time, because it was the most stable state to measure. In this test, we were able to hover for just over 27 minutes. This was higher than the simulation, which was expected because the computer was not included in this flight test. This in turn made the drone lighter, so we were able to exceed the simulation time.
In order to verify that the drone was capable of following a car at a moderate speed, we tested to see how fast the drone could fly by being stable. In the video you can see our pre-flight checks before the actual flight. Being we lacked a radar gun to measure the speed, we just did a standard mathematical speed test. We did this by measuring out 150 feet and flew it as fast as we could and recorded the time. Our goal was that we wanted to be able to fly at least 20 miles per hour. Mathematically, that comes out to just over 29 feet per second. To make sure that we can maintain its speed, we did this for a 5-second span of time to verify stability. Being it would only have to technically cross 145 feet in 5 seconds to verify the speed, we knew that less than that would match our design simulations. In the end, the drone was able to cover 150 feet in 4.65 seconds, which comes out to just over 20 miles an hour, which exceeds our design goal of 20 miles an hour. In this test, we confirmed its potential speed. Things that we noted while doing this test was the drone's high sensitivity due to its large size and weight. We flew it in a straight line, but due to momentum, it was harder to slow down at the end of the test. Being this project ultimately was going to be controlled autonomously, we were certain that the computer would be able to achieve even higher speeds due to its instant response time. The GPS accuracy for autonomous missions is critical in order to make sure that the drone can navigate waypoints. This was done by calibrating the GPS and flight controller in order to make sure that the telemetry data is always accurate. To verify accuracy, we tested in two areas, one being the gyroscopic stability and the other being in the GPS directional data. The gyroscopes were tested using a protractor. As you can see in the top left part of the video, this is where all the data for the drone's pitch, roll, and altitude are located. We tested the roll and pitch by using a protractor against the flight controller in order to confirm that the data feed matches the values being fed to it. We did this by putting the flight controller in 8 different orientations in order to ensure that there was no discrepancies in any one direction. For the altitude, we raised and lowered the drone 3 feet in each direction, and with doing this, we were able to see that the altitude gave us a plus or minus 3 inches of accuracy, which is exceeding our expectations. For the GPS directional data, we tested in 2 ways. First, we tested the location accuracy by walking 5 feet at a time while confirming its location was true by using easily visible landmarkers. This resulted in ThinkNav having a GPS accuracy of plus or minus 1 foot. To test the yaw accuracy, we used a compass to confirm due north and proceeded to turn at 45 degrees at a time. This was a little bit harder to confirm numerically because the data feed is only visible by the directional arrows seen in the video on the right. But we confirmed its accuracy by using small landmarks that were at least 25 feet away in order to confirm that it was pointing in the correct direction. This gave us enough precision measurement to allow ThinkNav to fly autonomously.
Shown below is one of our initial tests of the object detection algorithm on some toy cars in the Senior Design 2 lab. The algorithm being run here is actually MobileNet SSD and not the tiny YOLO V4 that we ended up going with, but it performs pretty well and gave us a good proof of concept running with very high frame rate and being able to track multiple cars with no problems. So even though they were toy cars at a very small scale, it showed us the potential for the device to be able to track multiple cars from a distance. Now, scaling up, this actually doesn't apply as much as we would like it to because of the limitations of the distance that the depth AI camera can handle with a maximum accurate depth reading of about 10 meters. So at scale, it wouldn't be able to really be as far away from cars as we would like, and this is something we would like to improve on in the future.
This project did not come without its own set of challenges, ranging from normal life events all the way to natural occurrences going through the scientific process of testing. First major obstacle was the loss of a sponsor. We took on a project presented to us from a professor who would sponsor us if we took up the project she presented. She had an unfortunate family emergency and had to leave the country 3 weeks after we took her up on that offer, which led to communication issues, and ultimately she ended up resigning. Due to this, we lost our sponsor and one of our intellectual resources. Due to swift actions of our team, we were able to secure a new sponsor through Dr. Reza and the electrical engineering department. Also, with the help of Dr. Ritchie, we were able to tailor our project to give us a higher chance of success with the absence of the original professor. Next, we had programming issues due to using an off-brand single-board computer. We originally chose it as a suitable replacement for the NVIDIA Jetson, but after several attempts, we were unable to get it to function properly. Luckily, the NVIDIA Jetson came back in stock and we were able to resolve the technical issues. When we attempted to order our original parts for the body of the drone, such as the frame, battery, and motors, there was a communications delay in our order request, followed by an order processing delay. Each of these added just over a week to the delays. In the end, the parts ended up coming in 3 weeks after we ordered them, when we expected only about 4 days tops. Lastly, our challenges was a mechanical failure due to accidents during testing. Out of all of the problems, this was one we expected and prepared for the most by buying a spare frame and propellers, being that they were the most common incidents in these types of experiences. What we didn't expect was the loss of nuts and bolts due to vibration. The biggest issue was the propeller nuts coming off mid-flight and causing the drone to come crashing down. Losing these nuts doesn't seem like too big of a problem until you realize that they have reverse threads, which makes them significantly harder to replace. Overall, due to our diligence, swift actions, preparations, and the cooperation and understanding of the UCF staff, we were able to overcome these trying issues. Our project was close to equally divided among 3 main categories, which were the drone body, the flight controller, and the computational hardware. Each of these 3 categories were equally important to accomplishing the mission. The computational hardware was purely the things outside of a standard multi-rotor build, and were the brain that made our drone autonomous. The Oak D-Lite camera was an upgrade from our original camera because we thought that it would be necessary in order to give the code the best chance of success with higher quality data. The flight controller was the most expensive thing on the build because it was a kit that gave us the GPS and all the necessary connections to bridge the gap between the computer and the drone body. Last was everything necessary to physically be able to lift the computational hardware into the sky. For this portion, we put more of our budget towards the battery and the frame to make sure it was able to stay airborne for a long period of time and was able to sustain multiple crashes from different elevations. We ended up subdividing our project in order to maximize our efficiency as a team and to maintain focus on individual goals. We split our 4-person group into 2 teams, hardware and software. By doing this, we allowed for each group member to have a focus and a partner they work alongside with.
From Group 12, we thank you for watching our presentation, and this is ThinkNav.